lectures. We get on to this new stuff, this second lecture. And like the thing I did last week, I'm going to break this up because I've got a bunch of different stuff in here and in different components. So I'm going to start talking about scale to begin with. Specifically, I'll talk about linear scale, then I'll talk about area in a separate recording here, and the same thing with detail and distance and all of that. All right, so that's the plan. So let's get into map scale. Okay, a pretty simple concept, but one, like so much of the stuff that we're gonna play around with in here, one of those things that you don't necessarily think about enough to make sure you're doing what you should be doing with it, right? So that's what we're gonna get into here. So scale, it's one of those things where if you don't pay attention to it, you might be picking the wrong map for what it is you want to do with that map. And I would have, in some of my just incredible teaching skills, I would have had you guys, play around with scale at the beginning of the class period. As we get into the lab, I'd be handing you out some maps, and then I'd be asking you to find something specific, and I'd yell at you for doing it incorrectly. But of course, the whole thing is I'm giving you the wrong maps. That's why you can't do it properly, and I keep feeding you better maps, and you see it gets easier. It's teaching brilliance, if I do see so myself, and it's an excuse to yell at students, which I love to do. All right, but so yeah, we don't have that ability in this remote setting with me talking into my computer here. Don't have that ability to force you guys to get thrown right into this, but you can get a sense. But I mean, this example here, using a globe to find your way around campus, yeah, that's a pretty obvious one, right? Even just trying to navigate in Southern California, pull out a globe, you're gonna see Los Angeles, maybe San Diego labeled, right? Maybe Las Vegas, and that's about it. And that has to do with the scale, right? How we're taking reality, what's out there in the actual world, and we're shrinking it down into map form or, as a globe or whatever. And it's basically how much are we going to shrink reality by, right? That's the idea. That's what scale is. So it's our definition here, our working definition for this, is it's the ratio between the size of a feature on a map and the size of that same feature in the real world. All right? So again, we've got the real world. We can actually measure, how far it is from point A to point B in reality. But then if we're going to represent that in map form, well, how much are we going to shrink that by? And the key thing here, if we're working with maps that are actually useful in terms of navigation or any kind of scientific analysis, they have to have some kind of consistent scale going on, right? That ratio has to be consistent throughout the map in order for us to be able to actually use it. So it's not just the ratio, but it's the fact that that scale is consistent in every corner of the map itself, or all over the globe, or whatever. All right, that's a key deal. And as I said, again, if you're not paying attention to what that scale is, you could wind up making horrible mistakes as you're trying to find where it is you're trying to get to, or you're trying to analyze stuff or locate something, or whatever it might be. So we have 3 different ways of reporting the scale of a map. All right, so it's that ratio between what's on the map and reality and all that. But there are 3 ways in which we will actually express the ratio. And typically on a map, we're going to have each of these 3 ways on there, right? So it's not a case of you pick one and that's it. They all work together. It's just they all mean the same thing. They're simply different ways of doing that. The first way, that I'm going to show you anyway, is what we call the verbal scale. And that one it's the easiest to think of, right? You don't have to think in terms of really numbers or abstract concepts. It's written out in a way that just makes sense in our everyday brain. So like this example here, 1 inch equals 1 mile. And when I say this, I kind of flinch a little bit at the equals because I had one professor. I don't even remember exactly which one it was, but I remember one would always get hung up on the idea that you can't put equals because it doesn't equal. That's logically that's impossible, right? 1 inch can't equal 1 mile. Those are different things. It's always stuck with me, but I've never thought it was a big deal. What we're saying here, of course, we're not destroying space and time and all that and making 1 inch equal 1 mile and everything's upside down and cats are marrying dogs and all that. No, it's just saying on the map, you measure 1 inch. That, what this professor would have wanted you to say was this 1 inch on the map represents 1 mile in reality. I say equals. We can all say equals. We know what we're talking about here, right? So I measure 1 inch on the map. What I'm measuring, that same distance on that map, if I look in reality, it's 1 mile, right? Pretty straightforward, and that's really useful too. If you're using a map, like say out in the field, you're hiking around somewhere in the backcountry, you're doing some kind of research or just having fun or whatever it might be. I measure the trail, the route, whatever, and I measure 5 inches, right? I know, okay, I got 5 miles to go. That's really easy for us to think about, to have work in our brain. So it's good in that regard, but it's not always the best way to go about this, right? And so that's where we have some of these other ideas. We have the graphic scale or a graphical scale. It's a scale bar. It's typically what we call it, although they're not always these linear bars. And again, this initial scale stuff I'm talking about, it has to do with linear scale, meaning miles and kilometers and stuff like that, right? Walking or driving or whatever it might be from one point to another, as opposed to aerial scale, where we're actually measuring, large areas of land, say, right? Kind of the difference would be like thinking in terms of roads, which is what we're doing with linear scale. Aerial is more like, real estate, pieces of property and stuff like that, right? You want to know how many acres is this piece of land that I'm looking at buying or, whatever it might be. That's aerial scale. So that's the difference, okay? But anyway, back to the linear stuff. With the graphic scale, it's a scale bar, pretty straightforward. And you're looking at this on a screen of some kind. So it's, kind of hard to say. I'll always try to be clear with this stuff as we're doing this virtually. But the idea would be that the distance between that 0 and number 1 on here, if you measured it, would be 1 inch, right? And then the distance from 1 to 2, that would be 1 inch. And what's great about this, it's the exact same thing as our previous verbal scale, 1 inch equals 1 mile. But with these, and this one's pretty simplistic, but it's a visual thing. So it can just help people who, they need that visual cue rather than hearing something or just seeing the words themselves. They like something a little more graphic, so that's helpful. But we'll see and we'll play with in here. There are some more complex scale bars where they just make it a little easier to figure out some of the nuance on the map, right? Not everything is going to exist in perfect inch or mile increments. And so some of these with little extra subdivisions and stuff like that can make it, useful, more useful to use this than that verbal scale. All right, that's the idea there with that one. And I'll always be clear too. I don't know if I was clear about this when I started explaining it, but if I'm asking you to do something on an assignment, a quiz, or whatever, I'll make sure that if we're not actually, using a map that I've given to you that I know is at that proper scale, I'll make sure to stress that the distance between that 0 and that 1, it's 1 inch or it's 1 centimeter or whatever it might be, right? Just so you know exactly if you get that graphic scale, and I'm specific with that stuff, you can convert it to the verbal scale, right? That's the idea there. And then finally, our third way to express scale, so we call a fractional scale, or a representative fraction. And so this, you've seen these things on maps, I'm sure, but you may not have ever really known what exactly does this mean, right? What's going on with this thing? So a fractional scale, it's really straightforward. It's really useful. This is really the best of these three in terms of what it gives you, but at the same time, it can be terrifying to initially look at. So we have right here the number 1, and then we've got the two dots, the colon right there. We read that as 2, as in T-O. So 1, 2, 63,360. Okay, now this fractional scale, it's exactly the same as the other scales. The verbal scale I showed you and that graphic scale that I showed you. So when I said that 1 inch equals 1 mile, this is the exact same thing. But with a fractional scale, what it's doing is it's keeping the units consistent on here, right? So it's 1 inch to 63,360 inches, okay? Or what's really cool about this one is I don't have to stick with inches. With this American imperial system, I can do the metric system, right? On this exact same map, 1 centimeter on the map is equivalent to 63,360 centimeters in reality. Right? If I measured a foot on the map, if the map's big enough, and I measure 1 foot, it would be equivalent to 63,360 feet in reality. 1 meter, 63,360 meters in reality. I could put my index finger on the map, the tip right there. That distance, one of those index fingers on the map, is equivalent to 63,360 index fingers in reality. So we got some flexibility with this stuff here. Now that said, how many inches are in a mile based on what I've said? Pause, think about that for a second. You can pause this if you want to do it. I've kind of given it away. You might not have picked up on it. You don't have to go to Google or ask, your phone robot to tell you how many inches are in a mile or whatever. It would be 63,360 inches, right? Because we had that verbal scale. We said 1 inch equals 1 mile. And at the same time, we're saying 1 inch equals 63,360 inches in reality, right? So that's how we can figure that out. And that's going to be useful as we move forward and we play around with some of this stuff. Okay, so the fractional scale is really, well, it's not the easiest to look at or to kind of initially conceive of. I mean, if I tell you, hey, could you do me a favor? Could you go walk, 64,000 inches? Just go walk that real quick. I need you to do that for me. Do you really know what I'm saying? Does that really mean anything to you, right? As opposed to if I said, hey, that thing we need to check out, it's about a mile that way. Can you go check that out? You at least can conceive of what a mile feels like, right? If you've got to hike that, walk that, or whatever. Whereas if I say, 63,360 inches, we got no reference. We don't, unless you absolutely know, oh, that equals a mile. You don't necessarily know what the hell I'm talking about. So that's why we use all of these together. And it's good to be able to convert back and forth. Okay, so here they are together again. So on a good map, you would ideally have all of this stuff written out, okay, so that it's clear, or at the very least, you want to have that fractional scale to start with, maybe with a graphic scale as well. The verbal, you can kind of figure out if you got the graphic, but ideally, we're going to have all three on a map because it just makes life easier so you don't have to overthink stuff. Okay. Now with this is what I was just saying before, but it's worth stretching here. So with this fractional scale or the RF scale, representative fraction thing here, the key thing that students often forget or don't pay attention to or whatever as you're working with this stuff is that the units are going to be the same on either side. So whatever measurement I'm doing, inches, centimeters, whatever it might be, it's going to be consistent, right? So this 1 to 24,000, it's 1 inch equals 24,000 inches, not 1 inch equals 24,000 feet, right? So just keep that in mind. Keeping these units consistent, it's incredibly important as you start working with this stuff. And be aware too, if you're doing, like map stuff that we're going to be doing, topographic maps and all that, you're going to see, that 1 to 24,000 scale that we just saw, going to see that a lot. We're going to work with that a lot. If you start doing, engineering stuff, architectural stuff, working with AutoCAD and actual plans and stuff like that, they tend to do things differently. Engineers and architects think differently than geographers, surveyors as well think differently than geographers, people who, start out in geographic analysis as opposed to surveying. But you'll see different things on there. And I've seen too with students will get confused with this stuff. And this also goes into just as you're trying to convert. If you get a verbal scale of 1 inch equals 400 feet, sometimes your instinct is just to put the 1 and the 2 dots and the 400, right? That's, I don't know, because it's scary and you give up and all that. But think about that. It's not the same thing. That would actually be 1 inch equals 400 inches, which would be totally different, right? It would actually be, if you're going to convert that into this fractional scale, which again, a lot of architects, they don't like that stuff on there, but we geographers do. It would actually be 1 to 4,800, right? Because if we take that 400 feet, we know there are 12 inches in a foot, and so therefore it's 400 times 12. You get 1 to 4,800 or 4,800 right there, right? So just it's not crazy math here, but you need to be able to work across different units and be comfortable with both metric and the American / imperial system of inches and feet and all that. All right, now with that graphic scale, okay, here's an example here. As you're using this stuff, which we'll eventually be getting to, so we've got, you can see our fractional scale up here. But if we look at the graphic scales, we actually have multiple scales here. So one in miles, one in kilometers, and one in yards. That's also very helpful. So you can, do basically so you don't have to do conversion with this stuff. And so if you need to think in terms of kilometers, great. You got that. If you need to think in terms of miles, you got that. And the yards is just if you're not, if you're working in smaller distances, basically that can be handy as well. Or some of these also might have, one that's in feet versus one that's in miles, right? But a key thing here with these more complex ones is that 0 is not at the end, right? So we've got a 5 here, 0 there, 5 and 10 on that top one for the miles graphic scale. So what's useful here is that you've got on the left of the 0, you've got those little smaller subdivisions, right? And if you count those, you'll see there are 5 in there between that first 5 and the 0. And so if there are 5 there, there's 5 miles. Each of those is 1 mile, right? They're 1 mile subdivisions and then 5 mile main divisions on that graphic scale. That's useful for when you're measuring stuff. We'll play around with this when we get to it. If I have you guys measuring stuff virtually here, it's kind of hard to do this stuff on computer screens and all that. But the idea is, if you're measuring on a map, and say again, we'll just do the point A to point B. distance, very rarely is it going to be perfectly 5 feet, right? Or in increments of 5 or whatever. It's going to be something weird. It's like 6.5 or whatever. But what you can do is as you're measuring stuff, rather than say, how can I make, God, this sucks. Not being able to just show you guys in a lab class, but it's the idea that if you're measuring across there, like you can use a piece of string or you can make marks on a piece of paper or whatever, where you can hold it against the point A and stretch it out to point B and mark on there. And so if you've got that distance marked on whatever it is you have on a piece of string, a pipe cleaner, that's something we use sometimes because they're kind of easy to use. Piece of paper, whatever it might be. Instead of holding that piece of paper up against the zero and then reading over to the right in this case, right? So putting it up against the zero on one end and then seeing where it falls, at 5, 10 miles, whatever on the right there. Instead of doing that, start it on, say, like if it's less than 10 miles, right? But it's more than 5 on your paper, like you can just tell that's the case. Or maybe you set it up on the zero and you read to the right first. You say, okay, it's somewhere in between 5 and 10. I really can't see. What you do is then just move it over, put it on that second 5, the 5 to the right of the zero, put one in there, and actually read to the left, right? So that the other end of your marked piece of paper or whatever goes into those subdivisions and it's just easier to see, right? You say, oh, okay, it's in the middle of that second subdivision to the left of the zero, so it's got to be 6.5 miles, right? Something along those lines. I don't know if that made any sense to you as I'm describing this. I'm waving my arms around a lot right now. You can't see any of it, but that's the idea. We'll play with it. Yeah, we'll try. Some other things that you might find. I don't anticipate we're going to play with any of these maps throughout this course here, but you have some where instead of having a nice simple little graphic scale that's a line like we just saw, you have something that's more like an hourglass like we see here. And this has to do with different map projections, which I'll cover, I think, next week. I get into that or the week after that. But it's when we go from taking the round Earth and we project it onto a flat piece of paper, you get some weird stuff that takes place. And with some of these, you get a distortion where the distances between 2 points, they change depending on where you are on the map. So what it's showing is down at the equator. So we're looking at latitude, which you guys are experts on after that last week of lectures, right? So the zero would be, the equator, 0 degrees latitude, and then we go 45 degrees north, 90 degrees north, that would be at the North Pole, right? 45 degrees south here, 90 degrees south, that would be the South Pole there. It's just showing that maybe, let's just say this is 1 inch from here to here equals 100 miles at the equator. But if you move up in latitude, either, northward or southward, right, as you move poleward, the term we use, but if you're at 45 degrees north, it's not 1 inch equals 100 miles. Maybe it's 1.5 inches at this point equals 100 miles. And maybe up here at the North Pole, it's actually 2 inches equals 100 miles. All right, so if you see something weird like that, it's a more complicated graphic scale. It's letting you know, hey, pay attention to not just, the distance here, but when you're measuring stuff, make sure you're aware of the actual location on the map to know exactly what that scale is at that given point. All right, hopefully that makes sense as well. Okay, another thing, we're playing around with scale. This is kind of a backwards deal, but we can have large scale maps or small scale maps. And it's kind of got this backwards concept, but it makes perfect, it's logical. But a large scale map represents a small area, okay? And a small scale map represents a large area. And this is always in relation to another map, right? if we're going to say it's a large scale or a small scale map. But like a map of the world, that's a large area, right? So that would be a small scale map. A map of Los Angeles compared to that map of the entire world would be a large scale map because it's representing a much smaller area. All right, but if you take that same map of Los Angeles and then you also have a map of I don't know, Quartz Hill, whatever, here in the Antelope Valley, that LA map would be a small scale map compared to our Quartz Hill map because the LA map is a larger area, the Quartz Hill map is a smaller area. Right? That's the concept there, and what it has to do with is the actual, the fraction itself. If we think of it as a fraction, that fractional scale. So you can see here this, 1 to 2 versus 1 to 4. It's the idea that it's 1/2 is the fraction there versus 1/4. So it's the idea that we call that a larger scale, meaning the fraction itself is bigger, but by definition, it's going to cover a smaller area. You don't need to stress about the math and the fractions and how that works, but that's just, if we say large scale map, we're talking small area, right? If we say small scale map, we're talking about a large area. That's really all you need to get for now. Yeah, same thing. It's just more math proofs in there. We don't need to worry about that. Let's get to the fun stuff, shall we? Look at this. Look at this right here. And we would do this together. It's a one big happy class, but we're all in separate locations listening to this at different times and all that. So I'm just going to let you guys play around with it and also let you know that you're going to have an assignment this week where you're going to have to do the same kind of deal as you're working along here, right? So, pay attention. We'll go through this and I'll set it up to where I'll kind of work through it. But then, hopefully you can also, just as you're listening to this, watching this stuff, you can pause, think about it. You try to do it and listen to what I'm saying, right? See if you're getting it. What I've got here is this little grid here of some scales. We have an example of a fractional, of a verbal, and a graphic. But at the same time, we've got these blank squares in here. So what we're going to do is we're going to figure out, okay, if we get this fractional scale, what's the verbal scale? What's, for that specific fractional one? And therefore, what's the graphic scale? And that second line, we get the verbal, but we don't have the fractional. So how do we go that way, right? That's how we do this stuff. So to start with this fractional scale that we get, we've got 1 to 100,000. Okay, so we remember, because we're all good little geographers here, that when we're dealing with this stuff, the units have to be the same. And you can see here, we've got miles and inches and stuff like that. So with this one, we're just going to work on the imperial system, the American system of inches and miles. So we'll assume that that's saying 1 inch is equivalent to 100,000 inches in reality. Now you might be tempted when we say, okay, what's the verbal scale? You might want to write, okay, 1 inch equals 100,000 inches. And to that I'll say F minus, no, I don't know what the hell that means, right? 100,000 inches. That sounds like a lot, or maybe not. Like an inch isn't big, but is it big? I don't know. It doesn't make sense. So I want it in a way that I can, it makes sense to me, right? So I want you to take that 100,000 inches and convert that into miles. All right. So what are we going to do? What's our process here? How do we even do that? You can pause now if you want to play around with it. See if you got it. Did you get it? You feeling confident? You think? Okay, well, let's find out. So what you want to do? If we're saying it's 100,000 inches, well, we want to convert that to miles. So we're going to divide 100,000 by say it with me, 63,360, right? Because that's how many inches are in a mile. And so if we do that, well, you're going to get a horrendous number right here, where it's 1.57828283 on my calculator here. We can round that. It's all kind of garbage. You can say it's 1 inch equals 1.6 miles. If you really want to be fuzzy, you could say 1 inch it's about 2 miles if you want to round up. I would stick with the 1.6 with this to let us know it's roughly, if anything, you would say it's roughly a mile and a half, right? And that's the thing with the verbal scale is you can get away with some of this it's roughly kind of stuff because you're just trying to get an idea of, okay, how far is this thing I need to get to, right? Or how long is this thing I'm studying or whatever it might be. All right, so let's see. I'm going to see. This is going to look absolutely awful. Here, I can do pen. Let's see if I can. Well, this actually looks, nope, I blew it. We'll just do that. Equals, a little trackpad here. This is looking great. When I say 1.6 miles. This is falling apart. There we go. Look at that. Look at that. It looks like a 4-year-old drew it. So there. Beautiful. We got that. And then for our graphic scale, what are we going to do, people? How are we going to make that work? How does that happen? So if we do, that was awful. But let's just kind of mimic what's down here. And we're going to assume that the distance from here to here is 1 inch, right? And this from here to here is also exactly 1 inch and perfectly straight and all that, right? So if that's the case, it would have a 0 there and then a 1.6 and 3.2, and you could do miles down there, right? It would look something like that. Or if you want to be really cool, you could have the 0 there and the 1.6 there and a 1.6 there. And over here, you could divide this up into units, but it's such an ugly number, it kind of doesn't matter. But you get what I'm saying, right? That's another thing you could do, but that's the idea there. Okay, we got that one. God, good work, team. We're doing a great job together here. What about the second row here? We get the verbal, so we know that 1 inch equals 4 miles, but what's our fractional scale? We know it's going to be 1 dot dot, right? But what's the big magical number there? How do we get that? I'll pause, let you figure this stuff out. But what would we do? Shout it into your phone or your laptop or whatever. Right, perfect. We would multiply 4 for 4 miles times, I should really have a mouse here, 63,360, right? So that's a times, even though it kind of looks like a plus, just trust me. All right, so 4 times 63,360 because 4 miles, that many inches in a mile. We multiply that. I can't do it off the top of my head, so let me go through my wonderful calculator. Oh, beautiful number. 253,440. 40, good enough. Yeah, all right, because that's 4 times 63,360. All right, not the prettiest number there, kind of a scary number. And so you can see why if you have something like 1 inch equals 4 miles, that can just be more comforting. It can make more sense. But having this it makes it easier to go if we need to go from say, this imperial system to metric stuff or things like that. And you also get to a point, if you work with these things long enough, you don't even need the verbal. Okay, 1 to 100,000, an inch is about a mile and a half, right? We have these consistent numbers that you're working with. We don't see this 1 to 253,440 on like USGS maps, but you will see some that are 1 to 250,000. Nice rounder number, and so okay, that's roughly 1 inch equals 4 miles, just about around there, right? That's the idea. And of course, with the graphic scale, same deal here. Draw one of these things. I'm not going to do it, but it would just be 0 and 4 and 8 and 12. And keep going on. Every inch will be a perfect inch. You guys are doing great. I'm very proud with how you're doing. I want you to know that. All right, for this one, we'll have the graphic. Verbal should be easy, right? Again, assuming this is 1 inch right here. We know it's 1 inch equals what? 25 miles. Oh, I'm going to have carpal tunnel. Yes, beautiful. So 1 inch equals 25 miles. To get this bad boy right here, we do what? Well, just look, what do we do here? We multiplied the miles by this number. Let's do the same thing down here. So it'd be 25 times 63,360 equals a gigantic number of 1,584,000, and then just 3 zeros. Yeah, that's kind of nice and round and pretty, although hard to draw. All right, so that would be that one there. Does that make sense? Hopefully that makes sense. Yeah, as we go through, but that's how you would convert back and forth with these things. All right, so there's that one. Oh, what the hell happened? We got another one of these because it was so much fun. We learned a lot together, working through this stuff. How can we not do it again, right? But you'll notice on this bad boy, we got some of this scary metric stuff, right? What them Europeans like to use. It's so much better. It's easier to think of. It's not based off of like the King's Anatomy and things like that. That's where we get a lot of these American things that we use. It's weird, archaic stuff. But with the metric system, it's nice and it's round and it's in units of 10, and at the same time it scares the hell out of us because we get exposed to it early on, but not enough, or at least I certainly didn't. I haven't seen a lot of my students get that. I will say one of my kids, actually my middle boy, he will refer to things in meters, and it blows my mind how he thinks in that way because they're doing all this STEM activity stuff. So that's kind of what he thinks of. Now, whether he's correct or not, like I don't know if he's saying meters, but he means feet or what. I haven't tested it on him. I might test him this weekend, see what he's doing there. But yeah, maybe if you've been properly conditioned in school, you think in terms of meters and liters and all the metric stuff there. If you can go with it, because as you'll see, it's a lot simpler. All right, so we've got the verbal scale here, same idea, right? This 1 to 100,000 that we've got here, it's the same units on there, and we need to get the verbal, but now we're going to think 1 centimeter equals 100,000 centimeters. All right, but it's verbal. We can't, even if you don't know what a kilometer is, it's a lot easier to think in terms of kilometers as you're doing this stuff than telling me to go hike 100,000 centimeters or whatever. So what we're going to do, 1 cm equals, what the hell is it? How many centimeters in a kilometer? Does anybody know? You know this? They didn't teach me that in school back in the dark ages. You can Google it if you want. It's really great. There are 100,000 centimeters in 1 kilometer. So I'm not even going to do any math. I'm just going to write this like that, right? Oh my God. Do you remember our 1.6, 1.5782828283? That was ugly. This, super simple, super beautiful. So 1 centimeter equals 1 kilometer on a map with this scale. It also, at the same time, 1 inch on this exact same map is going to be 1.6 miles, right? Because that's the cool thing with the fractional scale. Now, if we have that, we can easily, go to different, measurement systems and all that, right? So that's the cool thing there. And then for the graphic scale, we'd mimic this, assuming that's 1 centimeter perfectly between here and here, and between here and here is another perfect centimeter, and so on. So we draw the same kind of deal, but it would be just 0, 1, 2, 3, 4, 5, and so on, right? Little centimeter increments, each going up a kilometer, for every centimeter. Hopefully that makes sense. All right, so that's that one. I'm not going to draw it. So this middle guy here, 1 centimeter equals 40 kilometers. You can do this, my little metric maniacs here. What are we going to do? We're going to put this 1 dot dot. And then, oh my God, what is the thing? We know the thing. It's so easy, right? And we've got the 4 and the 0 here. And then we know the 40. So that's times 100,000. And it's all in zeros and stuff like that. It's going to be fantastic. And what you can do, you know the rules, right? When you're doing this stuff here, is you just add these zeros onto the end, right? So let's put 5 more zeros on here, and I'm going to try to make sure I do it properly, not do extras. Let me do my little commas here. Beautiful. So our answer there would be 1 to 4 million, right? Would get us 1 centimeter equals 40 kilometers. I didn't even have to pull out my calculator. That's how easy and simple that was. Thank you, Europe. Thank you so much for the metrics. I assume it came from Europe. They use it there. I feel like a real ass if it's Chinese or whatever. No, but I think it was all Enlightenment stuff. Thanks, Europe. All right, so that's that. Does that make sense? And then the graphic scale, same deal. Okay, the 0 to 10 right there, we know based on this graphic scale, we're going to do this. Oh, my battery's dying. So, okay, I'll finish this up. So that would just be 1 centimeter equals 10 kilometers, right? And then you can figure that out. The 10 times 100,000. You guys got this. Super, super easy. Hopefully that makes sense. And like I said, you're going to have this assignment. We're going to do a little bit of that stuff. So, yeah, hopefully you watch this. It made sense. Let me know if you've got any issues with it. And yeah, it's a perfect spot to stop. So I'm going to end this now so my computer doesn't die and I don't lose all this incredibly important work. So yeah, stay tuned for more of this fun with scale and distance and things like that as I put it together. All right, talk to you later, geographers.